Hey guys, sorry our video cut off. Radius increases as we go to the left and down, as we were just discussing. So I want to tell you a little bit about why it does that. So as we move to the left, we get less and less protons. The atomic number decreases, gets smaller, and that's because there are less protons. The less protons we have, then the less force we have between the protons, which are in the nucleus in the center, and the electrons on the outside. So less positives here, okay, to interact with these, means it doesn't pull that outer shell in closer to itself the way it does when it has more protons, okay? So less protons means less force pulling the outer shell in. So more protons means there's more force to pull that outer shell in. So more force pulling it in means it's closer, so it's smaller. So less protons, less force pulling shell in equals bigger. Okay, more protons, smaller, and a greater force. So that explains why atomic radius increases as we move toward the left on the periodic table, but it does not explain why atomic radius increases as we move down. So I want to run through that with you really quickly. So atomic radius increases as we move down because as we go down, we're adding more shells. Okay, so as we move down, we're adding more shells or energy levels. More shells, energy levels. Same thing. What is an energy level? Well, that's just one of the periods on the periodic table. So remember, the first period consists of hydrogen and helium. Second period, and we have the third, fourth, all the way down to the seventh. So we have 7 total periods or 7 shells. So as we move down, we get more shells. Remember when we drew those Bohr models and we kept adding more shells as we went? Well, the more shells we get, the bigger it is. So more shells is bigger. So that's why atomic radius increases as we move down. Now, I want to go through some examples with you guys real quick. So remember that ionization energy, I'm going to abbreviate here, electronegativity, we'll call that EN, and electron affinity. All of those follow the same pattern. They increase as we move up and increase as we move to the right. Now remember, if I asked you how they decreased, it would be the opposite. This is how they increase. So that gives us an overall pattern this way, angle pointing up towards that right corner. So that means that our higher values are going to be here, and our lower values are going to be here. So remember, a major difference in these three, okay, is that for ionization energy, the noble gases have the highest values. For electronegativity, fluorine is the biggest. So those are two to remember, super important things. And for both electronegativity and electron affinity, noble gases don't have values. Okay, so let's look at some examples we could possibly have. All right, so let's say we are looking at lithium and beryllium. Lithium, beryllium. If I ask you which of those two has the highest ionization energy, electronegativity, or electron affinity, the answer to that would be beryllium for all three. Why? Because we know that it increases as we move toward the right. Beryllium is more toward the right. Okay, that's because beryllium's more toward the right than the others. If I asked you which had the lowest, the answer would be lithium. Between those two, lithium would be the lowest for ionization energy, electronegativity, and electron affinity. Let's look at another example. Let's say we have phosphorus and arsenic. We know that all three of those trends increase as we move up the periodic table. So that means that phosphorus is higher up than arsenic, so this would be the highest in this example between the two. Arsenic is lower than phosphorus here, so it would be the lowest value between those two. And one more quick thing, what if I gave you something like, sorry about that, it's my cat. Okay, if we have something like fluorine and cesium to compare, opposite ends of the periodic table. Well, if we're looking at ionization energy, electronegativity, or electron affinity, all right, all three of those, fluorine is going to be higher. Okay, we can assume it's higher because it's closer to the top right corner than cesium is. So we would consider this one to be a lower value between those. All right, one more. Let's look at atomic radius. Okay, atomic radius is the exact opposite. Okay, remember it increases left and down. So it's a little different. So let's look at those as the same examples here. If we have lithium and beryllium, okay, between those, to ask you which one has the largest radius, lithium would be the largest. And beryllium would be the smallest. That's the exact opposite of the trends we were just looking at. And that's because this trend goes in the opposite direction. So lithium's more to the left, atomic radius increases to the left, so lithium would be larger here. Let's look at phosphorus and arsenic, same examples. Same thing again, so in this case, arsenic is going to be larger. Phosphorus is going to be smaller. Okay, and let's look at those cesium and fluorine here again. This time, fluorine is going to be smaller. Cesium is going to be larger because it's closer to that bottom left corner and follows that overall trend that we see with atomic radius. And that overall trend for this one is going down towards the bottom left corner. Exact opposite of what we saw before. So one more quick note on ionic radius, a little different. It's like atomic radius, but we can't compare it in the same way with trends. So with this one, we want to compare each atom to its neutral version as compared to its ionic version. So let's take a look at chlorine. We have regular chlorine, and then we have chlorine negative 1. So we know that chlorine forms a -1 ion because it's in group 17, right? So, and everybody in group 17 makes a -1. So a -1 means that it gained an electron. So it added an electron to what it had in its neutral state. So regular chlorine had 17 electrons. Now we've added a -1. So now we have a total of 18 electrons. So we added more. So that means that this atom is bigger. Okay. So negative means bigger because we added electrons. All right, so let's look at a positive ion. So we have regular sodium. Sodium's in the first column on the periodic table, and everybody in that first group, everybody in group 1 makes a +1. Okay, so the difference for this one, let's make that a little smaller. The difference for this one is a +1 means we lost an electron, we gave one away. So it has fewer electrons than it had before. So we're going to get a smaller version as compared to the neutral atom. So let's write that down. Positive means smaller because we lost electrons. So remember, these are always as compared to one another here. So when I say neutral, what does neutral mean? Okay, well, neutral refers to an atom with no charge. So regular chlorine here in this example is neutral. Chlorine -1 would be the ion. And that's because it has a charge. In our second example, sodium's neutral, and then sodium +1 here would be our ion. And this would be our neutrals. Okay, so chlorine is smaller than chlorine -1. Sodium is bigger than sodium +1.